So, questions? Questions?
Are you recording?
I am. I got the recorder. Natalie got the recorder to work again. So. Wednesday is the last big lab in terms of your unknown, in terms of gathering information. So by Friday, you should really have the bulk of the information you need for identifying your unknown. What I'm going to encourage you to do Wednesday is it probably won't take the full period to inoculate all of the media. And so I'm going to have you start looking through your key C1 to try to see if you can get it to genus right now with the information that you have. You might need some more information, but it's good to get started and kind of good to get that process going and start thinking about it. The other thing you could do if you have time available is I'll make sure I have some computers set out and you could start working on your ID Factor. Okay? Okay, a few things to finish up and talk about regarding infectious disease. Nosocomial infections. Have you ever heard that term before? Yeah, I mentioned it briefly. They're hospital-acquired infections. Actually, that's the terminology that's starting to be used more commonly now. HAIs or hospital-acquired infections. You've got about a 10% chance of getting a hospital-acquired infection if you have a hospitalization, and that's a little bit scary. That's about between 2 and 4 million cases a year. That's pretty significant. And that translates into about 100,000 deaths. So now we're getting really significant. Cost-wise, about $5 to $10 billion, mainly through extended hospital stays. There are a number of ways in which you can acquire hospital-acquired infections, but many times they are either the result of invasive procedures like surgeries or medical devices such as catheters, or also you can get them through passive transport between healthcare workers and patients. Most hospitals now have committees, oftentimes headed by a nurse practitioner, which are really trying to keep track of and keep a lid on these hospital-acquired infections. And one of the most effective ways that you can really deal with these is a very stringent procedure of hand washing. And they're getting better, but doctors are still a little bit non-compliant sometimes. Last time my wife was in the hospital, there were the alcohol hand cleaner dispensers everywhere. And I mean, I know the nurses were very good about hitting those when they came in the room and when they left the room, but I saw a couple of doctors who were not. And so this is still something that we need education-wise to get a handle on. This is just for illustrative purposes, but this shows you a breakdown of some of the organisms and some of the causes of these hospital-acquired infections. Notice that the biggest percentage are urinary tract infections, and a lot of the enteric organisms are involved in those urinary tract infections. Lower respiratory, fairly significant. Surgical wounds, unfortunately, still fairly significant. And so this is something that is really a continuing battle. If you think about it, a hospital is not a very safe place to go in terms of exposing yourself to unhealthy individuals. And I think that that's one of the reasons why these surgical sites are really becoming more and more popular. And sometimes they're a separate part of the hospital campus, but oftentimes they are completely off-site. And I think the idea is, let's not have surgeries, particularly elective surgeries like knee surgeries and things, where the people aren't really sick, but they've just got this mechanical defect that needs to be cleaned up. Why put them in a hospital environment with people who have all of these infectious diseases? And so that's probably not a bad strategy. And I think doctors have taken advantage of making some good money out of buying into those surgical centers and then using them for their practice. So it's definitely something that we need to keep a hand on. Okay, epidemiology. It's an ology, so it's a study of. What's it a study of? Okay, the cause, distribution, and spread of diseases. Basically, epidemiologists are medical detectives. And they're answering those classic questions of who, what, where, when, why, how. Okay? Who's infected? Where are the infections occurring? What is the cause of those particular infections? How are they being transmitted? One of the things that really drives epidemiology is data collection. And two things that are collected routinely about certain diseases, which I'll mention in a second, are the incidence and prevalence of disease. Incidents are the number of new cases. Prevalence are the total cases in the population, which would include new cases and existing cases. So this particular graph would be an example of a type of epidemiological data, and it shows here in yellow incidences per thousand, and then prevalence, thousands, of AIDS among U.S. adults. Okay, so you can see that the incidence is fluctuating, and that we reached a peak incidence in about 1993, and then it's slowly been kind of declining, but then we've got a little blip here and a bump here again. Okay, well, what's going on there? Well, one of the things that epidemiologists do is when they figure out what the cause of a disease is, then they oftentimes are involved in public health policy and education, trying to spread information about how that disease is transmitted and how you can be protected against getting that particular disease. And so a lot of the decline we saw here was a result of education and safe sex practices. Okay? But notice how the prevalence just continues to climb, because that is the cumulative total number of cases. And since you can survive a long time with AIDS, for the cumulative number of cases, you can go back years and years and years, okay, and people still have it that contracted that disease many years ago. Okay, some of the diseases that are more virulent, there's not that big of a gap between incidence and prevalence, because when you get it, you die. And so there are no existing cases once you die. So Ebola has a much smaller gap between incidence and prevalence. Okay, by law, there are 36, I believe, nationally notifiable, or they also call them reportable, diseases. So if you go into your doctor and he diagnoses you or she diagnoses you with one of these diseases, they must report it on and up the chain of command. Okay? And just a quick glance through here, you see that hepatitis A, B, and C are all reportable. HIV, chickenpox, okay, mumps, okay. These are all considered to be serious diseases that we need to continue to monitor and gather statistics on. So how does the flow of information go? Who does your doctor report to? Anybody know? Yeah, there's a county health officer. Okay, so each county has a health officer. Any of you worked with Dr. Mormon before in any of your rotations? The hospital? Dr. Mormon's a pediatrician. I believe he still is. I know he was in the past for a long time. The county health officer. So everything funnels in through Dr. Mormon. Okay. Then, who does he report to? Yeah, there's a state level position of a state health officer, and all of the counties report to that state. Okay. Who do the states report to? CDC, okay, that is our federal clearinghouse, Center for Disease Control, which is come under fire for their, people say, their lack of preparation for Ebola. Okay. CDC then shares information internationally with the World Health Organization. Okay, good. Every month, the CDC puts out a publication called the MMWR. Yes. I'm afraid to ask.
It's Hannah. What about the Surgeon Health General? What does he do?
Surgeon General? I don't know where he is in the loop of this particular thing. Good question. Never thought about that. Anybody know what the MMWR stands for? Actually, I was wrong. It isn't every month. It's every week. This is the Morbidity and Mortality Weekly Report. So for those particular 36 diseases, they report on trends, what are the incidents, what's the prevalence, how many people are dying, what's the distribution. And these particular reports are filled with a whole bunch of very interesting statistics, charts, graphs. So this is just some kind of selected examples of some of the kind of data you might see published in the MMWR. Okay, so here, foodborne botulism. Okay, West Nile virus activity by state. Pertussis, whooping cough. Okay, 2003 data by age groups. Estimated number of adolescents, adults and adolescents living with AIDS by state. TB cases. TB cases by age group. By ethnicity. Okay? There's all kinds of way to parse that particular data and report it. And this is something that public health officials rely on and really must keep current on to be able to kind of determine what's going on nationwide, what's going on worldwide with these particular diseases. Okay.
Do they take this information and see, like, for instance, like the Hawaiians don't really get this? Do they try and see what's the difference?
Absolutely, yes. Yep. Yeah. This is really only one part of what epidemiologists do, collecting data. We'll talk about some other kinds of strategies that epidemiologists and the CDC uses as well. One of the things that is very much of an interest to the CDC are changes in the incidence and prevalence of diseases over time. And many times they're very interested, for example, in seasonal changes. There are four kind of patterns that seasonal changes fall within regarding diseases, and those are endemic, sporadic, epidemic, and pandemic. You may know what endemic means? The disease is endemic to a certain area. It doesn't have to be catastrophic. It just means that there are a relatively constant number of cases in a particular geographic area, and year after year after year, those number of cases is pretty similar. So it's kind of a stable situation. Now, it can be a serious disease. Okay? So, for example, here, valley fever, is endemic to the Southwest United States. This is where you typically find them. There are a characteristic number of cases that are reported in those states year after year after year, and it really doesn't change much. Okay? Sometimes, however, those patterns can shift, particularly as vectors that transmit those diseases change ranges. That happened with Lyme disease. Okay? If you would look at a map of the distribution of Lyme disease, it would have been primarily decades ago right up here just in this northeastern corridor here. But as the range of the white-tailed deer has expanded, it has become endemic to more states now. It has spread. It's now endemic in Indiana. Okay? But that particular term doesn't really have anything to do with the severity of the disease. As the name sporadic probably makes sense to you, that's a situation where a case just kind of pops up. It really wasn't there before. We might get a few cases here and there, but there's really no predictable pattern to it like there is in endemic. Measles is sporadic now. Rabies is sporadic. Okay. The term that's probably most misunderstood and most misused is the term epidemic. Okay? What does that term conjure up in your mind, epidemic? Super widespread, right? The world's falling apart, I mean, it's really bad. Okay? Epidemics occur when the incidence and prevalence of the disease is greater in an area than history suggests it should be. So there's actually a statistically significant difference in incidence and prevalence compared to historical values. It says nothing about the actual number of cases. Okay? So if a disease had been endemic to a region over decades, and that particular number of prevalence was 200 cases, and all of a sudden it went up to 400 cases, that would probably be a statistically significant increase, okay? And now that would consider to be epidemic, okay? But there's this idea and this misunderstanding of that term that seems to suggest that you have to have huge numbers of cases, okay? What's pandemic mean? Yeah, this is when you have an epidemic situation on more than one continent.
So can an epidemic be located to one particular area, or would that be considered endemic?
No, in fact, epidemics are defined by geographic areas. Okay. So if a situation is endemic, if a disease is endemic to an area, and in that same area we get a statistically significant increase in the numbers, now that's considered to be epidemic in that area. Okay.
So an endemic could really be like anything, as long as it's like centralized. It doesn't even have to be like that much higher than the normal incidence.
Right. Yeah, it's got to be higher than it's got to be statistically higher than the normal incidence, and statistically higher what past history would have predicted.
But like the endemic, that.
Oh, endemic.
Yeah.
Endemic is when you have a stable situation. Okay.
Oh, right. Okay.
Okay. And an epidemic would be is when that situation becomes unstable. Okay. There are kind of three approaches to epidemiology, and kind of three kinds of things that epidemiologists as a whole group do. And one of the approach to epidemiology is descriptive epidemiology. And this involves kind of tabulation of information about the disease. What's the incidence? What's the prevalence? Is it increasing? Is it decreasing? Where are these infections located? What kind of infections are they? One of the things that descriptive epidemiology really strives to do is try to determine the index case, or patient zero, sometimes they refer to it as. Why is it important to know where patient zero is?
So you can figure out where it started.
You can figure out where it started, and then you get insights about how it spread, okay? How can you understand how it spreads if you don't know where it started, okay? So I think I read someplace that they think they have found patient zero for Ebola, Okay? And that's an important first step. One of the earliest studies that was done, sorry,
Why is the one combining patient zero rather than the source?
pardon me, what?
Rather than the source of the problem, like the water disease, like chloride.
Oh, well, it's important to know where the reservoir is, definitely, too. Okay? But if you don't know what patient zero is, it is very hard to determine method of transmission, because it's hard to trace then how it got from, even if you know it's reservoir.
But isn't that really the challenging part?
Oh, well, yes, the reservoir is challenging, but patient zero is challenging as well.
Is patient zero dead?
Um,
Probable.
I'm assuming so, but I don't know for
How
sure.
do you know it's patient zero?
I'm not. Ask Chickwana. Ask Chickwana how you figure out who patient zero is, since he's doing an epidemiology program right now. So that's your assignment. One of the first descriptive epidemiological studies was done in 1854 by John Snow, a British physician. I think I mentioned this when we talked about the history of microbiology. And this is the map that he did by going door to door in London during a cholera epidemic and knocking on doors and finding out who was sick and who wasn't sick. And as he determined the location of people, he found that there was a correlation between this one particular pump where the water was contaminated and then clusters of that particular disease around the pump. Another branch of epidemiology is called analytical epidemiology. And this gets really more into figuring out what the mode of transmission of the disease is. What is the course of the disease? How is it spread? And also then that could lead to possible preventative measures. Okay, if you understand the mechanism of transmission, then you could potentially come up with some recommendations about how do we stop this particular spread. So these are people that rely on the analytical data and then apply it to trying to answer those deeper questions. And then finally, there is experimental epidemiology. And these are people that are really into hypothesis testing. They look at the data, and they might decide, looking at the data, we believe that there is a particular type of bacteria that is involved in certain types of heart disease. But then they take it a step further, and they test that particular hypothesis. So they set up a group of control patients and experimental patients who have a history of heart disease, for example, and then they give antibiotics to one group. They don't give antibiotics to the other group. They then look at how many people come up with heart disease out of those two groups, look to see if there's a significant difference, and then that helps to determine whether their hypothesis is validated or rejected. One of the other things that experimental epidemiologists and analytical epidemiologists both use a lot are Koch's postulates. Remember, that's the logic you have to go through to correlate a particular disease with a particular pathogen. A big, huge part of epidemiology is biostatistics. And you really do have to understand statistics to be able to be working in this particular field. They're doing some crazy stuff in epidemiology, particularly at the CDC with some of their experimental epidemiology. And when you start working with some of these really nasty pathogens, then you have to work under these stringent biocontainment levels. You know, they're doing research in, basically spacesuits to try to keep from being exposed to these particular diseases. Actually, I have a graduate from the 80s who works at the CDC in experimental epidemiology. Would love to get him here sometime to talk, but haven't been able to handle it yet. So Okay, so let's shift gears. If I've done my job, by now you should be a little freaked out about pathogens because they have a pretty impressive array of offensive weapons that allow them to infect you. Now, remember that there's a series of events that has to take place before infection can occur. Number one, you've got to attach. Number two, you've then got to be able to penetrate protective barriers. Now that you've done that, you can multiply, and that's what infection is multiplication of organisms in the tissue. Oftentimes, these organisms have virulence factors that allow them to spread, and many times these virulence factors produce damage to the tissue, which manifests itself in the form of disease. The other thing that these infectious agents need to be able to do, though, is evade the immune system. And we talked a little bit about some of the strategies that they can use, like the antiphagocytic factors, or some of the toxic enzymes, like leukocytins, that kill the defending white blood cells. So there's really a warfare going on in your body constantly with your defense systems trying to thwart invasion and the offensive capabilities of pathogens. What wins usually? Your defense system usually wins. Thank goodness. Okay? With all the organisms that are out there in the world and the number that you're exposed to, it really is kind of amazing how your body is able to fight infection. And as long as your immune system is well developed and healthy, and you're not immunocompromised, then it is more the exception than the rule that you get sick. So now we want to look at the defensive capabilities of your body. And that's something we're going to spend several weeks on. Because really the last topic after we talk about that will be applications of some of these defensive systems to medical diagnosis and treatment. So we're going to dig fairly deeply into your body's defense systems.
You talked about rheumatic fever, you talked about cross-reactivity, like how it damages the heart. Is that fairly common with pathogens, or does it mostly
We'll get there. Yeah, it's not common. It's not common. So, let's give you a little overview first about your immune system in general. And this is a strategy I'm going to use a lot in this particular part of the course, is we will talk about big picture. And then we'll pull back and we'll look at some more things in detail. And then we'll go back to big picture again, so you kind of understand context. And then we'll pull back and look at some other aspects of it. So we're constantly kind of going back and forth between big picture understanding and then drilling back down and kind of really understanding in depth what's going on with certain aspects of this. Can we drill down in depth on all of it? No. We could easily have a full semester or probably a full year course in immunology. I'm going to try to give you some relevant detail for about 4 to 5 weeks. Okay? So we're really going to, it'll seem like in depth to you, but we're barely just scratching the surface of this. But it's very important to keep coming back to this big picture and kind of understanding holistically how all of this stuff happens. This is material that you really do need to keep up with. And so if you're not in the habit of printing off PowerPoint slides, if you're not in the habit of looking at my lecture notes, if you're not in the habit of keeping up with study guide questions, I would strongly encourage you to develop that habit for these next 2 exams. Okay? Also, I have the feeling that probably most of you are not taking advantage of your textbook that much. In this particular section particularly, I try to follow the textbook, not lockstep, but the textbook's pretty helpful in terms of if you read it before we start talking about a section, you'll at least understand some of the kind of big picture of where we're going. And so doing some preparation before you come to class really can be very important. So, big picture about the immune system. What's going on? Well, there are certain characteristics of the immune system that I think that you should be aware of. Certain parts of the immune system have a high level of specificity. And that's particularly true when we talk about antibody-antigen interactions. Antibodies are proteins. And they combine very specifically with an antigen. For right now, it's okay. I think if you think of antigen as kind of a foreign molecule, that's not entirely correct, but it's okay for context right now. So when antibodies see these foreign molecules, they bind to them and ultimately triggers elimination of those molecules. Very much like an enzyme-substrate relationship. Only certain antibodies will bind to certain antigens. By the way, it will be not uncommon at all for me to just write AB up on the board. If I do that, that's antibody. And AG is antigen. The word antigen literally means or refers to a molecule that stimulates the formation of an antibody. An antibody generating molecule or an antibody producing molecule. So these things cause cells to produce antibodies. Anybody know what kind of cells are involved in antibody production?
Is it B cells?
Yeah, there's a group of cells called lymphocytes. And B cells, or B lymphocytes, actually are the ones that produce the antibody. But more often than not, a partner cell, a T lymphocyte, is also involved in that process. Doesn't have to be, but it usually is. So there's specificity going on there. Okay? Yeah.
Like in proteins, are there like competitive issues stuff for antibodies? You know what I'm talking about? Did they bind to other things?
Theoretically, yes. Okay. So if something had a very similar structure to that antigen, it could bind as well. Oftentimes, it doesn't inactivate the antibody. More often than not, what's happening is two things can stimulate the same antibody to form, like the strep antigen and also antigens on your heart valves. Okay, so that's more of a cross-reactivity problem than a competitive inhibition problem. Okay. What's really cool about the immune system is that a part of it, the antibody-producing part, has memory. And that's the whole basis behind immunization. The first time that you are exposed to an antigen, it takes some time for your immune system to gear up and produce antibodies. And if that is a highly virulent infectious agent, you might be dead by the time your immune system gets geared up. Okay. But if you survive, you then have memory cells which can quickly produce antibody in a very short period of time if you have subsequent infections.
This might be a little bit off, but with the little chickenpox vaccine, why did it just like take them a while to develop it? Because like I know obviously like when we were still kids, like when people would come over so that they would get chickenpox.
Right,
or
yeah, exactly.
So, did they think that people were like dying?
They didn't really think that chickenpox was that serious.
Yeah.
And then once they figured out, for example, that shingles is the result of the latent chickenpox virus, and shingles is a serious disease, I can attest, then they started saying, well, maybe we shouldn't just routinely let our kids get these diseases. We should really immunize against them. And I don't know how long, it might have taken a while. Not all diseases are equally amenable to forming vaccines for. They would love to develop an Ebola vaccine, but they haven't been able to do it yet, obviously.
So does that mean the kids who are getting that vaccine are going to get shingles? Or a high probability?
You've got to get chickenpox. You have to have had chickenpox to get shingles later on. So if you've been immunized against that, it should really tremendously decrease your chances of getting shingles.
So these older people are starting to get shingles vaccines. So what would that be?
Shingles vaccine, I don't know exactly how it works, but it prevents the reemergence of that chickenpox virus from going into that new disease. Yeah. So will the shingles vaccine be necessary when we have this new cohort of people who have been immunized against chickenpox? I don't think so, but that's another good question. Yeah. You tend to get a stronger and more lasting immune response if your exposure to the disease was natural as opposed to an immunization exposure. So sometimes immunization exposures have to be boosted, and sometimes you will have to get a booster shot over time. Another thing that characterizes the immune system is redundancy. You know what that term refers to?
Just a repeat of efforts.
Yeah, it's backups basically. Okay, the U.S. space program, when we were going to the moon, really relied heavily upon redundant systems. Okay, what if your primary system goes out? There better be a backup. Okay, what if that backup goes out? Ideally, there's another backup. Okay, so duplication of effort, but it gives you a greater level of protection. The immune system is that way. There are several parts of it which kind of seem to do the same thing. Okay, those redundant systems can help reinforce one another, but also if you have a defect in one part of the system, then you can still survive potentially. Okay, so there are genetic conditions, for example, where part of your immune system is compromised. But the redundancy of your overall immune system helps to compensate for that, just like if your primary computer went out on your spacecraft. A lot of feedback associated with the immune system, both positive and negative feedback. Remember, positive feedback is self-reinforcing. And so positive feedback mechanisms are very prevalent in the early stages of infection, particularly when the bacterial population is in their log growth. You want a very robust response then against that. So the system kind of feeds upon itself and amplifies its response. But you want to keep that going forever. No, at some point you've got to shut down, right? And so many times that's when some of these negative feedback systems then kick into play. And at some point in time, the system turns itself off and resolves itself. Okay? You don't want a heater in your room that just constantly keeps producing heat, and the higher the thermostat gets, the more heat that's turned off. Okay? We want a self-regulating negative feedback system that at some point in time shuts itself off when needed, when the infection's been resolved. So that's important.
When I was at the hospital, my shadow had some kind of, someone had like a cytotoxic storm, and or cytotoxic storm, and they said that it was a positive feedback loop. I mean, I tried to look it up when I was there, but I didn't quite understand what that meant.
What that ultimately would mean is that whatever triggered this cytotoxin storm, like the superantigen that we talked about, toxic shock syndrome, that The cells are producing toxins to kill other cells, and then they're producing toxins, kill other cells, they're producing toxins. So it's kind of a chain reaction out of control. Yep, absolutely. Okay, when we talk about the immune system, I'm going to be referring to the immune system in terms of 3 lines. And this kind of silly little graphic right here illustrates those 3 lines of your immune system. And they are very ingeniously labeled line 1, 2, and 3. The first line of defense primarily consists of mechanical barriers that try to prevent infection from occurring in the first place. The skin being a very important part of your first line of defense. The second line of defense consists of cells. There are certain biochemicals, and there are certain processes. The first line is very nonspecific. It's not targeted as protection against a particular pathogen. It's trying to keep anything that's harmful out. Be it a fungus, a virus, a bacterium, whatever. The second line of defense is also nonspecific in terms of its response. Okay, it gives the same general response to a number of different threats. Some key elements of this second line of defense. There are various cells that are involved, particularly white blood cells. And one big part of your second line of defense are these phagocytic cells, which gobble up, ingest, and kill pathogens. So we'll talk about phagocytosis quite a bit. There are some chemicals that institute a defense system in your second line of defense. And one set of chemicals that we'll talk about that have a fairly interesting and complex interaction is a defense system called the complement system. Probably haven't heard of it before. Another set of chemicals that we'll talk about is interferons. You may or may not have heard of interferons before. Now, these chemicals are also produced by cells, but they aren't necessarily always white blood cells. There's some other cells in your body that can produce complement, can produce interferon.
Is stomach acid a first line?
Yep. Yep. First line consists of tissues. It consists of some chemicals. And there are actually some genetic components of the first line. A process that we'll talk about a lot in the second line is the process of inflammation. And I know you've heard of inflammation before, but you might not know that much about it. Inflammation is the result of cellular activities, most definitely, but there are a number of chemical compounds involved in the inflammatory response. So we'll talk about those. These two lines of defense are referred to as innate defenses. You're born with them. The third line of defense is not innate. That is something you build over time during your life. And this is where antibody production comes into play. This is where some cells of your immune system that actually kill your cells intentionally come into play. Now that seems a little bit destructive, doesn't it? For an immune cell to kill your own cells? Why would you want to do that? Yeah, if the cell is infected, if it's filled with virus, if you can kill it before it bursts open, that's going to help to prevent the spread of that infection. What's another kind of cell you want to kill? Yeah, cancer cell. Okay. And the mechanism ultimately by which these cells are killed is through apoptosis. Cells are triggered to destroy themselves, basically. So we'll talk about how all that works. So now we're talking about B lymphocytes, T lymphocytes, macrophages. So there's fairly interesting players in this third line of defense. This is the one that has memory as well. So that one's pretty cool. I'm time. So tomorrow we will pick up with continuing on this overview a little bit and then jumping into line one. Check your. Oh, yeah, you should, if you can, check your litmus milk today. If you can't, pop it in the refrigerator.